We're ready to go. Let's go. Go ahead, Maya.
Hi, everyone. My name's Maya. I'm a second-year PhD student at Northwestern, and I'm interested in precision measurement and fundamental science using molecules. Today, I will talk about my efforts along with ACME collaboration to answer questions that our current standard model of particle physics doesn't explain. Our universe is made of matter entirely with very little antimatter, and that violates what is known as charge parity time symmetry. And if we had what we known in regular physics, we would have had equal parts of matter and antimatter, and at the Big Bang, it would have annihilated and we wouldn't have existed at all. So particle physicists are trying to understand the reason why this is. And most physicists are looking for CPT violating physics using colliders like the LHC at CERN. But what our group is doing is looking at the electron, and it's which could possibly have an electric dipole moment. So explaining how the electron EDM violates CPT. If we reverse time, the electron, its spin will flip over, and this violates T symmetry because the spin is in the opposite direction. It's supposed to stay the same under this transformation. So this violates CPT. And if we put an electron in electric field, its energy levels will split, and but the splitting is too small to measure in a lab setting. So what we do instead is take a thorium oxide molecule. The reason we use thorium oxide is because it has a really high internal electric field. And if we put this molecule in electric and magnetic fields, the molecule's internal field will interact with the external fields, and it'll precess based on the magnetic moment of the electron and the molecule, as well as the effective electric field. And we have to do checks to make sure that this is indeed the electron electric dipole moment and not some other thing caused by inhomogeneities. So by doing that, we flip the molecule's position so it either faces upward or downward, or we also change the direction of the fields. And as you can see, the energies change based on these changes. So we've done this experiment a few other times, and the electron electric dipole moment has been measured to be 0. But our third generation, what we're doing each time is that we're increasing the upper limit and what is predicted to be in the standard model. And the bigger that it is, the more likely that it violates some CPT violating physics. So what we're doing in our third generation is we're making a few changes. So first thing we're doing is that we're making our experiment bigger so that the thorium molecule has more time to process and develop a phase, and that will cause the deviation, the upper limit, to be more precise. Another thing we're doing is we're increasing the number of molecules. Only a very few number of thorium oxide molecules make it to the chamber to be measured, and we want to increase this number by using some focusing electrodes and a molecular lens. And the last thing we're doing is we're continuing to use thorium because of its high internal electric field, but we're improving our collection optics at the end. And what I'm currently working on is making our magnetic field really uniform, and I'm working on building our cosine theta coil and measuring the magnetic field using magnetometers, which are a special type of magnetic sensor. And if you have any questions, I'd be really happy to answer them. Thank you. Everett, you're muted.
And I'm muted. Happens to me all the time. So yeah, thank you so much, Maya.
Thank you.
If
Marika
anyone has
a question, or are you just celebrating? Okay, thank you.
Yeah, definitely. If anyone has any questions, please speak now or forever hold your peace.
The questions can go over to the other platform so we can all hear them.
I'll exit or I'll stay actually, so you can hear me.
No questions? All right. Well, all right. Yeah, we'll move on to the next person. So let's go to the next one. Lorraine, are you you're up? Are you ready? All right. Go to the podium next to me and then you can start presenting.
Absolutely. I believe I'm standing next to you now, Everett.
Yep, I see you. Awesome. All
Excellent.
right, your PowerPoint is up.
Video games have finally paid off in a tangible fashion. Thank you so much for having me. My name is Lorraine M. Hare. I am a graduate physics student at Howard University. I am working on the Raman Cube rover project with NASA. We are currently working to achieve Raman spectroscopy at a distance. So to give a little background, Raman spectroscopy has been around for decades. It's been used as a method of laser spectroscopy to gather information on either unknown or known subjects. Typically what happens is we excite a subject with a laser, and then we take the information gathered from that. What we receive is a shift in the beam itself, and the Raman signal is collected. The shift is caused by Rayleigh scattering. So whenever a laser enters into a subject, the beam excites the particles around it. Those particles then react to that energy, jump up to a higher energy state, and when they jump back down to the lower state, the ground state, they then emit they emit a different signal, and that shift is what's actually measured. Our plan is to actually create Raman at a distance, so you could get that signal at about 200 to 300 millimeters. We can get it at most 1 meter. And our goal is to get that signal at an order of magnitude greater. That's the proof of concept we are working on. And long term, we want to go even beyond that. So right now, we're looking to get 1 meter, 10 meter is our goal, and then 100 meters is our overall project, our long-term abstract and thesis. What you see before you is the R-Cubed rover. It's basically a small rover that's going to go to the moon. With it is an apparatus that's going to allow us to collect this Raman signal, a telescope. And then from there, we're going to direct the signal over to our lander, which is going to possess the spectrometer, which is then going to measure the signal. We're working on 3 different methods to do that, either with a steerable mirror, a direct access or direct excitation of the subject, or we're going to be looking to have a series of lenses that focus the beam directly onto the lander, which is going to then determine what we have within the subject itself. Below on the bottom left-hand corner, what you see is recently received results for a quartz sample that we have within our laser spectroscopy lab at Howard. As you can see, we are showing around where we should be at 1 meter, which means our results are both accurate and they are exactly what we're trying to achieve to get to our long-term goal of extending that beyond 1 meter and into an order of magnitude of 10 meters. On the bottom right-hand corner, we're showing the division of work in our different segments, our T1, our tasks. And we're looking right now to complete task T1, TAC 4, which is actually building a rover, which is going to serve as our example for our proof of concept. In the middle there, what we have is our microscope, and what we're actually looking to do to collect the backscattered light, which is increase our A omega. And that would be my 3 minutes. Are there any questions?
It looks like you have one in the chat, actually. Oh,
Absolutely.
wait, no, I take that back. I'm sorry, that was actually your comment at 117.
Yes, I was asking Ms. Watts a question, but I think she actually didn't see it, and that's fine. I'll walk up to her and ask her later if she has time.
Oh, I did. I see it in the chat now. You were asking if they're made in the ground state. Sorry, but I'll let you do your thing.
Yeah, we can catch up afterwards, whenever you've got a chance, Ms. Watts.
Yeah, for sure.
All right. Does anyone else have any questions for Lori, though? Cool. All right. So thank you so much, Lori, for an awesome presentation.
Absolutely. Thank you for having me.
All right. So next up, we have Anthony. Are you available? I see you next to me. All right. Awesome. Yep, I see you. All right. Jump into the orange circle and then you can get started.
So you can hear me now?
Yes.
Okay. All right. So to start with, so this is my project, and I work with the Pierre Auger Observatory, which is the largest air shower experiment in the world, and it's mainly is there to set up for three questions. So the three questions are, where do cosmic rays come from? What particles are they made of? And how do they get here? So there's a problem in ultra high energy cosmic rays because this sets up questions of what are the particles like we get here at Earth? What are they made of, or where do they come from? So my main research question is actually the composition of these particles. So the POG right now is undergoing an upgrade, which is going to become the POG Prime Observatory. And with the Prime comes an addition of different components that are supposed to set up better detection and improve the detection that the POG already has. So it's been running for the past 20 years, and now they're trying to include radio to facilitate the detection of cosmic rays at the POG. And so what I do is I'll be using radio techniques to try and, at least I use radio techniques right now to try and find out the composition of the particles that we get here at Earth. So when a cosmic ray comes here, or at least enters the atmosphere, it has a point at which it has its maximum development. So in the picture, in the background, you can see that there's a part where it's at least the thickest part of the cosmic ray air shower, or the air shower itself. And so that itself tells us, the height in the atmosphere tells us what this particle may be made of. So at the bottom right, you can easily see there's a plot there that shows the current composition measurements. So for the current understanding is that the particles that we get here become heavier as we go up in energy. And so this is what I'm trying to untangle. So this is my 3 minutes.
Awesome. Thank you, Anthony. Does anyone have any questions for Anthony? All right, seems like we're good. Thank you so much, Anthony. Great presentation. Yeah. All right. So next up we have Nia. Nia, are you around? Oh, I see you. Okay. Go up to the stage and then go to the circle right next to me. There you are.
Unmute myself and then let me get the screen back up. Okay, cool. Hi everyone, my name is Nia. I'm a fourth year at Northwestern, and I'll be talking about my research, which is about short-range force sensing with optically levitated nanoparticles. So the basic goal of my experiment is to detect short distance gravitational forces. So we're talking about non-Newtonian, beyond the standard model type of gravity. And in order to detect such a small force, we need something really sensitive. So we use lasers and optomechanics to detect this. And so on the bottom left, the basic setup of my experiment is that I have a 1064 nanometer infrared laser, and it reflects off of a gold mirror. And we have a 300 nanometer silica bead that sits in one of the antinodes of the laser's wavelength. And so when the bead is sitting in the trap like this, it's not necessarily completely still. It's actually oscillating very quickly in 3 dimensions with a certain frequency that we can actually measure. So measuring that frequency, that's what that graph is showing in the middle of the screen. What that basically is showing is the frequency spectra, how it's moving in 2 different scenarios of vacuum pressure, and the signal to noise ratio reduces at higher vacuum. And you can see the resonance frequency of the bead in the axial direction in this graph. And so using this system, we've been able to show in the past that if we look at the bead in a trap like this and average over time, the sensitivity of this apparatus can be down to 6 septonewtons approximately. So that's really powerful. That's 10 to the negative 21 newtons. And so that's perfect for the really tiny force, gravitational force that we want to detect. So in order to detect a short range force, what I'm showing on the right is a drive mass being brought close to the setup that I was talking about before. And so if you take that mass, shake it up and down next to the setup, that will cause a small shift in the bead's position, and we can look at its frequency spectra and see how that affects the bead's position and in reaction to that small force. Yeah, that's it.
Yeah, really great presentation. Does anyone have any questions for you? Before we go to the next person. Cool. All right. Thank you so much, Nia. Oh, looks like that's a celebration too. Cool. All right, cool. So the next person, I please tell me if let's see. Yes. Okay. All right. Where is the next speaker? Are they not with us? Ah, yes, I see you. All right. Kachi, are you? Can you make it up here? All right, go up the stage. Can you go to the circle right next to me? Okay. Go straight. Oh, and seems like they disappeared. Okay, it seems like they are having some technical issues right now. Unless they plan on rejoining. Maybe not. Okay.
They're back.
They're back. They're back. All right. Awesome. Kachi, can you make your way up to the stage? So go straight. Can all right. Wait, give me up here. Up here. There you go.
Okay.
Awesome. All right. Are you good?
Yes. Yes.
Awesome. Perfect. All right. So your slides are up now. So start when you're ready.
Okay. Thank you. My name is Onyedi Kachi Alanwoko. I prefer to be called Kachi in short. But I'm a second year PhD student at USF, University of South Florida. This is something we did like about some months ago in the lab. So I just said, let me, try out the 3MC and all that. Okay. So I'm very sure you're all familiar with semiconductors. Semiconductors are very important materials that we use today. You can see some of its application in things like this, PCBs that can be found in our phones and laptops. And I mean, we should not be tempted to open our phones and laptops. They are definitely there, but you're gonna get spoiled if you do that. You also have some of the applications in like LEDs, light emitting diodes, which of course we use for our Christmas lights. And I'm sure we are all anticipating the Christmas. we also have like this application also in transistors and all that. So there are so many applications of semiconductors, and I can go on and on talking about the application and all that. So, but the important thing is, so even though this material I'm talking about is very important, there's some kind of difficulty that we face when we try to like connect it to some external circuitry, and this point of contact doesn't give us the performance of the devices that we want. So we if you take this important semiconductor device and we shrink it to a very thin monolayer material, which is something like as shown at the top right of the screen, we see that we can actually place metal contact on the material through like by putting it at the edge or on top of the material itself. So whichever be the case, there's always this high contact resistance that we have between the metal and the material. So it doesn't allow charge carriers to flow very easily between those materials, and therefore we don't have the good performance that we require in our devices. So in my lab, what we did is, because we try to like solve this conflicts between these two materials, we found a way to make some kind of neat interface between metal and a semiconductor. And what we did is we had so instead of bringing a semiconductor material and a metal together and having this creating this issue of contact resistance, high contact resistance, what we did is we had is a semiconductor material, and then we doped it and changed some part of it to a metal. So that way we had a very clean interface. So what we did is we had the platinum monotelluride material, and if you dope, platinum bitelluride, which is a transition metal like acogenides, when you dope that material with platinum, you get some part of it to be platinum monotelluride, which becomes a metal. So platinum ditelluride is a semiconductor, and when you dope it with some more platinum, you get a metal. So if you look at the image, there's an STM image that is shown at the top part of the screen, where you have arrows pointing at some regions. So those regions are converted regions. So when you have some of the areas which are platinum ditelluride, you dope with platinum, some of them are converted to platinum monotelluride. And then we have a kind of clean metal semiconductor contact. So if you look at the towards the left of the screen, where you have metallic TMDC and semiconductor TMDC, that is just exactly the kind of interface that we try to make from that image. So we see that metallic TMDC is forming a kind of clean contact with semiconductor TMDC. And we're able to do this by just introducing platinum, doping the semiconductor material platinum. And then that actually made some of the regions converted to a metal. So this is what we did, and then we are still currently studying the kind of interfaces and then using some spectroscopic techniques like scanning tunneling spectroscopy to like understand the kind of interface that this brings. But eventually, the end result is that if we can actually create an interface that is free of dipoles, surface dipoles, and all those things, that we can actually increase the performance of our devices, and then the contacts that we have with semiconductor materials can also be made better and all that. So, thank you.
Thank you so much, Kachi. Before we move on to the next person, does anyone have any questions? All right. It seems like we are all good. So yeah, all right, next person. Oh no, there is no one else. All right. So since we've now completed the 3MP session, whoever is judging right now, definitely convene on that. But thank you so much for all the presenters. This is sponsored by the Heising Simons Foundation. So thank you again. Thank you so much. I hope you enjoy the talks, and I hope you also enjoy the rest of Black in Physics Week.